General rule for polynomials of degree n $. Before we dive into the new material, let's take a moment to reflect on what we have already studied in our previous sections. You might recall that we have been observing a very consistent pattern regarding the relationship between the degree of a polynomial and the number of times its graph crosses or intersects the x-axis. For instance, we have already seen that a linear polynomial, which is a polynomial of degree 1, has exactly 1 0. We also observed that a quadratic polynomial, which is of degree 2, can have at a maximum of 2 zeros, and a cubic polynomial, which is of degree 3, can have at most 3 zeros. Now, the goal of this specific section is to take those individual observations and expand them. We are going to generalize these patterns into a single, fundamental rule of algebra. This rule is powerful because it applies to any polynomial, no matter how high its degree might be. So, let's move forward to see how this rule is formally stated. Welcome, everyone. Let's begin our lesson on the general rule for polynomials of degree n. Understanding the general rule. Now that we have reviewed the patterns we've seen with linear, quadratic, and cubic functions in the previous section, let's formalize this into a universal rule. On this slide, we are defining the core relationship between a polynomial's degree and its zeros. Specifically, if we have a polynomial, let's call it p of x, and its degree is n, then the graph of y equals p of x will intersect the x-axis at most n times. This means that a polynomial of degree n can have, at most, n real zeros. Now, that might sound a bit abstract, so let's break this rule down into smaller, more manageable steps so we can apply it easily. The very first step is, identify the degree, which we represent with the letter n. To do this, you simply look for the highest power of the variable x in your expression. The degree is always that highest exponent. For example, let's look at this polynomial. P of x equals 5x to the fourth minus 2x squared plus 1. If you look closely at the exponents, the highest power here is 4. Therefore, in this specific case, our n is 4. Keep this in mind, because as we move to the next slide, we'll see how this number acts as a ceiling for our graph. Relate degree to intersections. Now that we have identified the degree of our polynomial, let's look at what that number actually represents in terms of the graph's behavior. Think of the degree, n, as a ceiling or a maximum limit. Just like a ceiling prevents you from going any higher, the degree prevents the number of x-axis intersections from going any higher. It essentially sets the boundary for the polynomial's complexity. Specifically, this degree tells us the maximum number of times the curve is allowed to turn around and cross the x-axis. It provides us with the upper bound for the number of real zeros we can expect to find, which leads us directly into a very important distinction we need to make regarding the phrase, at most. Interpret the at most clause. Now, before we move on to a helpful analogy, I want to pause and focus on a very specific part of the rule we just discussed. The phrase, at most n, is absolutely critical to your understanding of this concept. When we say, at most n, we are setting a boundary. It means that the number of zeros can be exactly n, or it could be any integer less than n, and yes, that even includes 0. However, the most important part of this rule is that the number of zeros can never, under any circumstances, exceed n. So, while the degree tells us the maximum potential, it doesn't guarantee that every single potential zero will actually appear on our graph. Real-world analogy, the parking lot. Now, I know the phrase at most can sound a bit abstract when we are talking about algebraic functions, so let's step away from the math for a moment and use a real-world analogy to make this crystal clear. Imagine you are looking at a parking lot that has been designed with exactly n parking spaces. Let's say, for a concrete example, that the number of spaces, which we call n, is equal to 5. Now, think about the cars entering this lot. You could have a busy day where all 5 spaces are filled, with 5 cars parked. You could have a quieter afternoon where only 3 cars are parked. You could even have a completely empty lot with 0 cars. All of these scenarios are perfectly possible within a 5-space lot. However, there is one thing that is physically impossible. You simply cannot park 6 cars in that 5-space lot. There just isn't enough room. The capacity is exceeded. This is exactly how our polynomial works. You can think of the degree n as the number of available slots or parking spaces for potential zeros. A polynomial of degree n might fill all of its slots, it might only fill some of them, or it might not fill any at all. But just like our parking lot, it can never, ever have more zeros than its degree allows. This brings us to our next slide, where we will look at a specific mathematical example to see this rule in action. Illustrative example. Let's take a look at a specific polynomial of degree 4, which we can write as p of x equals x to the 4th power minus 5x squared plus 4. To really grasp how the rule works, let's perform a step-by-step analysis. First, we need to determine the degree. By looking at the expression, we can see that the highest exponent of x is 4, so our n equals 4. Second, we apply the general rule we just discussed. Since our degree is 4, the rule tells us that this polynomial can have a maximum of 4 zeros. Third, let's look at the geometric interpretation. If we were to actually plot the function y equals x to the 4th power minus 5x squared plus 4 on a coordinate plane, the curve would intersect the x-axis at most 4 times. Finally, let's perform a verification to see if the rule holds up. In this specific case, we can actually factor this polynomial into the product of x minus 1, x plus 1, x minus 2, and x plus 2. This gives us the zeros 1, -1, 2, and -2. In this particular instance, the number of zeros is exactly equal to the degree. However, remember that the rule says at most, not exactly. To illustrate this, consider a different polynomial of degree 4, such as p of x equals x to the 4th power plus 1. If you were to graph this, the curve would stay entirely above the x-axis, meaning it has 0 real zeros. Even though the number of zeros is 0, the rule is still perfectly satisfied because 0 is indeed less than or equal to 4. Now that we have understood the theory and the parking lot analogy, let's put this rule into practice with an illustrative example. As we move to the next slide, we will discuss some common pitfalls to avoid when applying this concept. Common mistakes to avoid. First, let's talk about the danger of confusing exactly with at most. A very frequent mistake I see is students assuming that a polynomial of degree n must have exactly n zeros. While we saw in our previous example with the degree 4 polynomial that it is possible to have exactly 4 zeros, it is not a requirement. Remember the parking lot analogy we discussed earlier. Just because there are 5 spaces doesn't mean there must be 5 cars. Similarly, the correction here is to remember that a polynomial of degree n can have any number of zeros, ranging from 0 all the way up to n, for instance. Think back to the quadratic polynomials we studied in earlier lessons. A degree 2 polynomial doesn't always have 2 zeros. It could have just 1, or even none at all. Second, there is the mistake of ignoring the real zeros constraint. Some students mistakenly believe that the graph will always reveal every single possible zero of the polynomial. However, we must be precise. The geometric interpretation we are discussing refers specifically to real zeros. As we touched upon briefly in our previous examples, if a polynomial possesses complex or imaginary zeros, those values will not appear as intersections on the x-axis. When you are looking at a graph, you are only seeing the real-valued solutions. Now, before we wrap up and look at our final summary, I want to pause and address 2 very common pitfalls that students often encounter when studying this rule. It is crucial to clear these up now so you don't lose marks on exams. Keep these distinctions in mind as we move to our final slide to review the key takeaways. Key takeaways. First and foremost, remember the fundamental rule we've been discussing. A polynomial, which we call p of x, if it is of degree n, will have at most n zeros. To put this into a visual perspective, as we saw when we looked at the graphs earlier, the geometric meaning is that the graph of y equals p of x will intersect the x-axis at a maximum of n points. It is very important to keep in mind that the degree acts as a limit. As we discussed with our parking lot analogy, the degree provides the upper bound, or the maximum possible number, for the number of real zeros. It does not tell us the exact count. It only tells us that the number of zeros can never exceed that value. To wrap everything up, let's look at this summary table which organizes everything we've learned. When the degree n is 1, we call this a linear polynomial, and it has a maximum of 1 zero. When the degree n is 2, it is a quadratic polynomial, which can have a maximum of 2 zeros. When the degree n is 3, we have a cubic polynomial, with a maximum of 3 zeros. And finally, for any general polynomial of degree n, the maximum number of zeros will always be n. All right, we have reached the end of our lesson. So let's bring everything together with our key takeaways to ensure you have a solid grasp of this concept. As long as you remember that n is your ceiling, you'll be able to navigate any polynomial problem with confidence. Great job today!